So this sheet here calculates the torsion and shear for each wall. So we have the stiffness and centre of mass computations here. So we have the wall thickness, that's to calculate the centre of mass. So if there's going to be different mass per wall, so we can change that around. The total stiffness of each wall is inputted here, then divided by the total stiffness of all the walls combined to get the centre of stiffness of the building. And then you get the area times the distance and so forth to get the centre of mass of the building. So then that can calculate the amount of torsion that's actually happening. So for the direct shear, again, it's just, as you said, it's the individual divided by the total stiffness of that to get the proportion of each. So now to get to the torsional component on each wall, as you said, it was Fi equals moment times D, or the eccentricity, times K I J divided by the total J. So for the moment, I'll just put down a 1 kilonewton multiplied by EY, so EY being the centre of stiffness, take away the centre of mass Y coordinates to get the moment on the building, and then the D is the individual distance from that Y component. So if you look at here, be 0.32 metres away, and then multiplied by the stiffness of that wall divided by J, and that's the torsional component on that wall. So for some of these, as you can see, some are going to be positive and some are negative, as they all get add up to 0, which they have here. So on here, we've got the final results of each wall. So for the cases where they were positive plus a minus, which should be less conservative, I just took the most conservative, which might be the torsion plus the shear, or might have been just the torsion and so forth. And then this is all based on 1 kilonewton. So then you multiply that 1 kilonewton by the total wind force, or the total earthquake force. And again, this is just only for one floor. Here we've got our earthquake and stability comps. So the earthquake modification factor 0.3, probability of exceedance 1 in 500, KP factor of 1, hazard factor of 0.08. So these are looked up from data and tables. Around here, so you got the hazard factor for each region, so that's linked to the input page, and then the Z factor is from the exceedance in probability, which is also one of the inputs, so it just looks it up from there. Next, we've got the KT. We're taking all other structures, so which is clause 6.2.3. So all other structures. For the building height, that's taken just the number of levels multiplied by the floor-to-floor height, and the natural period can be calculated from some of the other numbers from earlier, as in the code. Spectral shape factor, which is CHT, which in the code is here. So for the natural period of 0.5 seconds in our case, I've just got a smaller version of this table in the spreadsheet. So it looks up data and tables C37 to I44. So it just looks it up here, puts the bin wherever we sit, and then looks up where we are based on the inputted soil types for each different soil. So I think we were strong rock and we were 0.5, so it goes to conservative side, so it goes up to 0.3, so it should spit out 2.35. I hope so anyway. No, 2.94. Is that because 2.94? Oh, because we said BE here. So in BE, yes, so that's correct. So 2.94, so BE, sorry about that. Structure type, so again, this is around the clause 6.3, so shear walls for timber. I don't know where that went. So for timber structures, so these are just the inputs from this table here. So where shear walls, we might need to change that to brace frames actually. I think it's more shear walls for the cases that we're in. And this works out to be about 5% of the dead load and so forth. So that, and then we've got the base shear here as well. Now for the wind loading, similar comps, we've got just the location, the exceedance of probability, and then I've got a bunch of just conservative, got all, most of these are 1, and then 46 meters per second. You've got the leeward, the windward wall, and the leeward. So this will minus each other, so it ends up being 1.5. So the windward 1 minus 0.5 is 1.5 for the aerodynamic shape factor. And then, so we end up with about 1.6 kPa for the load. And based on the floor to floor height, these are the different loads at each level for the wind case. So here we have the stud design part. So this is linked to where you input from the input page, where you have stud type A, stud type B, stud type C. So whatever they input here, it goes straight from the page and so forth. So these are the inputs. Here we have the design. So all the assumed K factors. Important to note, and I've also got bending and combined actions here, but important to note at the moment, for all of them, I've assumed no eccentricity. So this might change and this might considerably change the results if you wanted to include eccentricity in the design. But you can go through here and then have a look at the comps to see if they match up with what you think and if it looks at about right. Here is the capacity per stud, and just below that, that's the capacity per meter, taking into account the spacing of each stud. So now this is the design. So now we've got the stud design, so we've got the capacity, we've got the load at each level and so forth. So first we've got the lateral loads for each level, and this takes it from here, which is one level, for the amount of load on each wall for one level. So this just does it more cumulatively. So that's the bottom level and so forth. As you go up the building, it decreases. So this is for the 5-story building at the moment inputted. Then it has the critical load case as well, it says there. Next is does all the loading combinations. So here are different load cases, and this again is linked to the front page with the dead load and live load we put in and so forth. Sorry, this is the capacity for the different load combinations. The different load combinations, sorry. And the next one's the capacity for the different load combinations with a different K factor giving different capacities for each. As you can tell here, the vertical load case, in this case, governs the design. And then here we have the required stud. So it's the capacity per unit meter. So it's the load divided by the capacity, and that gives, and then it's rounded up. So it could be conservative, where if it works out to be 1.1 or 1.2, then it's rounded up to 2. So that might be conservative, but I think might be sufficient for the purposes of this tool. And again, so this is for the ground level, and then as we move up, level 2, level 3, level 4, 5, 6, 7, 8, 9, 10, and I've just made it 0 when it's less than the input levels is less. So that does the design, and that spits out the spacing of each in the input page. So that's how we get to here. So the next part is how we got the comps on the number of studs per linear meter and volumes and all this kind of stuff. So here we've just got the stud type. We put in the number of stud comps, which we just worked out, and this is the number of the number of leafs. So if it's discontinuous, there's going to be 2. If it's single, there's 1. So it just looks it up, and whatever you input, it changes. So if we look at south wall here, for example, if we made that discontinuous, which it won't be, but we'll just for the purpose of explaining it, this will change to 2. So then there's all of a sudden twice the amount of studs there. So then total studs here is just the wall length divided by the spacing multiplied, that's the spacing, multiplied by the number of studs per leaf, and so forth at each level. So that's the amount of studs. So it's quite a lot of studs in this building. And then it does that for each level. And then for each type, so this just counts the amount of studs of each type. So for type B at level 1, you're 2,100, 2,100 there, and so forth. So it just counts it per level of what stud type we have. And then at the bottom, it has the number of studs of each. And then we just multiply it by the floor-to-floor height. So I multiplied it, I allowed 400 for structure here. So the stud length is the floor-to-floor height minus 400. So it's a little assumption I put in there. And then that gets us the total linear meters we have. And then on the output, on the input page with the outputs, that's what is spat out here. So the number of studs in the linear meter, and then the total volume of each, which is 111 meters cubed in this case. So the next part is we're calculating the total wall footprint of each stud type. So again, you input the single stud, discontinuous, and so forth. So for a single stud, the wall depth is going to be less than the discontinuous double leaf. So I've got it in here somewhere, I think. So this is just the total wall depth here. So this stud, so this is the gap, and this is the plasterboard. So this is the whole build up. So you got discontinuous, you got 4 layers of plasterboard plus 20 millimeter gap, and then I'll input the studs part later, so forth. So it's 72 build up without the studs of discontinuous, and 52 for the others. That's the assumption there. And then it just, that's the depth without stud, and then it just adds the stud depth multiplied by the number of leads, and then it multiplies that by, so that's the total wall depth, and then multiplied by the whole wall length, and that gets the total wall footprint per meter squared, and then it's just added for the whole entire building for each wall, and that gives us the total wall footprint. So, you know, as you, on the user input page, as you toggle around with this will change the amount of wall footprint per level, and so forth. So for the bracing, the different bracing system options, they can all be found here. So if you go to the input page, so here, whatever they choose, say heavy stud frame, medium stud frame, CLT or concrete, the calculations can be found here. So for the lightweight, this can be found in the EWPAA website and the manual. They've got these, but so for 3.4 kilonewton per meter capacity bracing system, works out to be 2.35 millimeters per kilonewton, and so forth. And the K factor then is 0.425, and also for the medium stiffness, I took as 6 kilonewtons per meter bracing system, and heavy 8.7 kilonewton per meter bracing system. For the concrete, I took it as based on a 2 meter length wall, as opposed to inputting the core as a whole, which would dramatically increase the K value of the core, but just to be conservative, I just took it as a 2 meter wall to be conservative. 200 thick, 3 meters high, and I'll link that to the floor to floor height as well, which that's meant to be. And so I took it as all uncracked. If it's cracked, it's going to be reduced a little bit, but it's already conservative, and that's taken in there. So this is just to get, you know, some rough numbers of what the concrete might look like for its stiffness. And then CLT, quite similar, based on a 2 meter wall. I worked out the length per meter, the stiffness per meter, and based on a panel in plane. So I just took the 45 plus 45 plus 45, and this is how I ended up at my numbers here. So that's the stiffness. And then for the material properties, they can all be found here for the different. So we can change this, and then this will change the front screen as well. Everything else is pretty much irrelevant except for F-C. F-B would be irrelevant if we included eccentricity in the comps, but that's about it. Please, if you've got any questions or queries, please let me know, and we'll try and amend the spreadsheet to suit. Cheers.